Welcome to the keynote Challenges and Opportunities in Rebalancing of Bike Sharing Systems. We're going to talk about bike sharing systems and the unique problems they create that might be solved by our next speakers. Our speaker is an expert in computer scheduling. He does research about bike sharing, a hugely dynamic system with his own weird and unique challenges. Yi Wu.
Thank you. So should I start?
Yes, please. Take it away.
Okay. Thank you for the nice introduction about the bike sharing and the bikes in Netherlands. So good morning, good afternoon, and good evening, depending on which part of the world you're coming from. So today I will talk about challenges and opportunities in rebalancing of bike sharing systems. I'm from the Temporal University, situated in the Philadelphia, Pennsylvania, in U.S. So as you know that in many countries, there is an initiative called Smart Cities, launched in different cities. So mainly the Smart City deal with management of assets, resources, and services, basically by collecting data, making decisions. So there's a long list of scope in this smart city projects. So today I will focus on about transportation. There are many other interesting events there, but we just focus on the bike sharing. So what's a bike sharing system? We know that bike has existed for many years. And nowadays they have a bike sharing system all over the world. So someone calculated there's over 1,600 bike sharing system with over 1,000 cities in over 50 countries. And if you look at the number down there, you see the number of bikes is like exponential growth over the years. In fact, there are lots of smartphone apps, shows the map apps and Google Map. You can find the location of this bike sharing system. So what's the benefit of that? One is the healthy life, right? So you're doing exercise, and it's green transportation. In fact, someone studied that 40% of BSS users drive less. So they tend to use bicycle more often, especially in Europe, in Asia, like China, and North America, like in US. So there's one issue about the usage of bikes in the bike sharing system is unbalanced usage. And in the diagram, you can see a map of Manhattan. And blue means that the return events, red means the rent events, means that you pick up a bicycle with the red, and then you return the blue areas. You can see that in the morning, especially when you're going to work, and in the eastern part of East Village part of Manhattan, you see lots of events because lots of residents there. They're picking up a bike in the morning, then in the afternoon. Then the situation is reversed. So you may have a situation so-called underflow, means that bike stations run out of a bicycle. Or overflow, when there are no slots left. And so this poses a real challenge in time and space. How can you rebalance those bicycles in the cities? So today we'll focus on the rebalancing of bicycles from the computer scientist point of view. So let's give some little background. So there are two types of bicycle system nowadays very popular. One is called automated BSS or dock BSS. On the right-hand side of the picture, you see a docking station. One is overflow, like full of bikes, and the other one is underflow. There's no bike left. But each bike, you place each bike in a station. And there are many systems, so I don't go through this one. Like in Philadelphia, where I lived, there's called Indigo, a company. They offer this kind of service. I also list a couple of other areas. And there's another type of bike system called dockless BSS, meaning that you can place a bicycle anywhere, or you can drop bicycle anywhere. Now let's focus how we do rebalancing or repositioning. There are mainly two types. One is using trucks, although it's not eco-friendly because you have to deploy trucks and move around. And we focus on through workers, the user themselves, through the cross-sourcing idea. So we'll discuss this later. So let me just give an overarching overview of such a system. In general, when you design a bike sharing system, you have to decide the location and the number of bikes in each location. So this is so-called a facility allocation problem, like a mathematical problem. So computer scientists come up with some kind of different algorithms, right? And another thing is that when you decide this location and the number of bikes in each station, you have to get some kind of prediction. Means that what's the demand, right? The prediction is very important. Actually, prediction is important when we do load balancing or repositioning. And we already mentioned that the main part is the third part is the rebalancing. So we need to look at two schemes. One is a truck-based, the other one is a worker-based. Actually, we come up with some kind of incentive-based mechanism. And also there is a planning and scheduling. It means that from which station move a bike to another station, and which route you should take, and so on. And the last one is even more interesting if you look at the global picture. So this system can provide called a trip advisor. It means that if certain areas that is too crowded, means a bicycle, probably you should give advice to maybe to recruit a worker to move some bike, or some area that run out of bicycle, then you can suggest the user to go to other area, nearby areas. So let's focus on this rebalancing. Before we do that, we know that nowadays AI is so popular. We call it AI takeoff. Right? So right now you see the convergence of AI with many other areas. For example, you can have XAI. X means high performance computing, or X stands for network AI convergence. So obviously there's solution, AI-based solution for the bike rebalancing as well. But one thing I just want to caution you that right now, DARPA, which is one of the military agency in US, launched an interesting project called Explainable AI. So AI is like a black box. It gives a very nice solution. But if you want to know the more detail, so people, researchers now spend time to study, right, how this AI works. So we need come up some kind of explainable model for human to understand. So today I will focus, instead of AI, focus on traditional algorithmic or combinatoric solution. I give you some kind of intuition. Obviously, this approach can be combined with the AI machine learning solutions. So let's look at the one specific example. Start with rebalancing through trucks. So basic idea is that probably you know that from mathematics, Hamiltonian cycle means that you find a circle, right, goes through each location. So we call it the Hamiltonian cycle. So just trucks move around the station from one station to another, going around a circle. Then the truck can pick up or drop off bicycle. Obviously, truck has its own capacity limit. That makes things more interesting and challenges, right? For example, each truck can put maximum 50 cars, right? So you need to pick up some bicycle and drop bicycle at a certain place at a certain time. So in general, we have an indication, make it simple, is that each station we label plus means overflow by M, like plus M means that you want to pick up M bicycle from that station. And the minus M means that it's underflow by M. You need to drop some bicycle. And trap capacity is L, for example, 50 bicycle maximum. Right? So this one, the idea is that you try to alternating positive and the negative. Positive pick up truck and drop some, pick up a bicycle and drop bicycle, certain location. and you have to go through in a Hamiltonian cycle. And you see this diagram that shows a very clear picture. For example, start from 0, you pick up 2 bicycles, and you go to the next station, you need to drop 2 bicycles. Then you just keep on picking up and dropping, right? And until you finish the whole cycle. So this is like a basic model. And let's just look at a couple of existing solutions for that. You see, the challenge is that you don't want to make the truck is like a full bicycle exceeding the capacity. At the same time, you cannot have a truck with an empty bicycle to draw bicycle. Right? So you need to keep the boundary of these two situations. So one solution is that suppose you already have a Hamiltonian cycle, you already have a cycle. Then you also know the capacity. What your idea is that you divide this area into pieces. So you have a cycle, you divide into pieces. One is called positive pieces, the other one is negative pieces. Positive means that it's an overflow, right? Negative is underflow. So your idea is that you alternate positive and negative, right? So that you will not have a situation is exceeding the truck capacity or zero capacity of a bicycle in the car. So one solution is that the so-called matching. So you first cut the pieces, positive pieces and negative pieces based on the truck capacity. So once you have this kind of pieces, obviously we can have a zero piece. Zero piece means that it's balanced. Right? So you see the diagram on the right-hand side, you have a color white, it means it's a positive piece. Dark means that the negative piece. And the size of piece is based on the capacity. Then what you to do is just matching a positive piece with a negative piece. So keep it balanced. And what we do the matching is so-called the perfect matching. Minimum weight perfect matching means that you try to keep the matching pair close to each other in terms of distance. And you want to minimize the overall distance to save time. Then you just still go through the Hamiltonian cycle. But when you do a Hamiltonian cycle visit, you visit the pair, one positive, one negative, in a certain way. So this is one solution. And this solution has a complexity of n cubed. Means n is the number of bicycles. And it can achieve a constant bound of 6.5, meaning that this, compared with the optimal solution, this has a bound. Another approach we call grid. It's a slightly different way. It's also divided into piece, positive and negative, with a different kind of capacity constraint. But the matching process is different. Suppose you start with a positive piece, then you go around a clockwise direction, find the next negative piece. So then from negative, you go around the clockwise direction, you find a positive piece. So you can see the second, on the right-hand side, the second picture, you start with the positive and negative, then positive and negative, and so on, until you visit each pieces. So these are two different algorithms with different complexity. But these two algorithms can apply in different scenarios. So in which scenarios? It turned out that the matching process works well for an area that relative sparse, and also in a relative geo area. If you want to balance bikes in a small area, this algorithm works well. For the greedy algorithm, the grid, it works well in a dense mode and in a relatively large area. So then we come up with ideas like maybe we can do is some kind of two-level hierarchy. So you divide a big area. In the right-hand side, the picture shows a map of Beijing. So divide into a small area. Within the area, which is small geo area, you use a matching algorithm or match algorithm. And then the truck can go from one area to another area. So you look at each area is like a one node. Then you apply the grid algorithm for the intercluster routing. So it's a two-level routing. So I'm not going to go through the detail, but just to show you the performance on the table. So we did a simulation in the city. City means that the center area, and the suburb is two outside area, and compare with match, grid, and hybrid. It turned out the hybrid performed much better in terms of distance-wise. Means that what's the total travel distance to balance the bicycle in the area. Suppose you use one truck. Okay. And also I list a couple of papers, including one of our paper as a reference. If you're interested, you can follow those results. So now let's look at the second topic, which is more interesting. That will be our focus. Is that the trucks, right? You have to rent a truck and you have to schedule that. Can we do through workers, meaning that the user, bicycle user themselves, can we use them to balance the bicycle? So that's a very interesting idea. Let me just give you an example. You look at the right-hand side, the top. So suppose you have a user U in that location, and this user wants to go to U prime, the other location. So you have a source location, destination. That's a normal situation. Ideally, if you can find a bicycle just near your home, ideal. But what happens if within a certain area, for example, within a couple block, there is an overflow of a bicycle? I put a small circle with plus, meaning that the company prefers someone can move to a particular location. So what you can try to do, ask the user to do a little detour to pick up the bicycle. From that location, you drop to your destination. Right? Assuming your destination also is underflow area, means that you need a bicycle. Obviously, you can extend this idea to detour in both the source and destination, right? So that means the user can detour in the source, a detour of alpha location distance. Then also the destination dropping area, not necessarily is what you want to go, but it's within a short distance. We call it L minus alpha. So the total detour distance is L. Right? So the idea is that assuming that user is willing to do a little detour upper bounded by L, but with some kind of incentive. Right? So there's some interesting research going on is that suppose neighbor is willing to do a detour, but with some kind of cost in mind, means that if I do a little more detour, I will ask a little bit more a reward. Right? From company point of view, what is the company to pay some kind of price, whatever, or maybe some kind of credit or some kind of cash reward. So they need to calculate the price. So this is kind of economic model. Right? So this pricing could be vary, depends on time and location. So there are lots of interesting research going on. You can see that and economic model. So what's the pricing and what kind of good mechanism to incentivize the user to help to rebalance the bicycles. So let's look at the one big picture. That's one of the research we did a couple of years ago. So in the early example, I just showed that you have one user to rebalance one bicycle. What happened that you have many users at the same time, right? And also many bicycle you need to rebalance. Again, use plus means that you have overflow situation or location, and minus in the diagram means that you have overflow or underflow. So what you need to do is to send one bike from overflow plus to a negative. And at the same time, you have a user, you have a bunch of users. So this actually turned out to be NP complete problem, means that it's a hard problem. And then what you need to do is to find out for matching. You're matching plus and minus, and also you need to match a bicycle with a user. So we come up with so-called 2 rounds of perfect matching. So the idea is you first match a plus bicycle with a minus bicycle. Once it's done, then you match user with that bicycle. And we prove that there is a constant approximation, means that compared with the optimal solution, we have a constant ratio. So, but this big picture is very important, so that when you do balance, you don't look at one piece at a time, you look at the global picture. Now, the next one is even more challenge. Means that in the early part, we only focus on the matching a particular time moment or time slot. But the problem is that bicycle rebalancing takes over time, right? Time means that morning situation, afternoon, and evening. And so this diagram shows a New York City bike data set. Just give you an example. So the color, the yellow color means that the peak, like lots of demand. You can see the workday's peak usually is during the work hour, like beginning the morning and late afternoon, there's another peak. But weekend peak is different. It's more even, right? Because weekend people do not go to work and come back home. It's just like a shopping. So that means that you balance, you have a different time scale. You can balance based on the day, based on the hour, based on minutes. Right? So we come up with this kind of ideas called static dynamic reposition. So it means that early on, we focus on one particular time slot and how do you do balancing. But if you look at the over time, then you have to balance over time. So it's multiple slots. So this makes the problem much more challenges. So in fact, this kind of ideas is the subject of this so-called distributed systems. So in fact, I just do a little commercial of my book, published last century, 23 years ago, about distributed system design. So distributed system really deal with like a time and space. So the diagram I showed the bottom there, you can see the horizontal line means the time, a vertical line means the space. So you have like three stations, and you have a slanted arrow, which means that you want to move a bicycle from station 1 to station 2 at a particular time slot, T. And you have this dotted vertical line really means a particular slot, right? And then in the next slot, you may move, you need to balance from 3 to 1 and 2 to 3 and so on. So this is a very interesting thing, is that how you represent this kind of bike rebalancing across the space and time. So there is many algorithms. I'm not going to go through detail, but just give you some idea. The question is that, can you do this one is like you look ahead, like instead of doing this one slot, you can maybe look at the couple of slots, K slot. So you want to minimize the move in current slot, right? So that this slot can last at least K hops, means a K slot. Or another one, you can do the greedy look ahead. Really means that you move the current slots, don't worry about the minimization, but this configuration can last longest one. Okay. So there's a different type of look ahead approach. So I'm not going to go through the detail of a simulation. So we did a simulation in both the time domain and the space domain. Space domain really means that you want to minimize the distance, right? Particular time frame. And we also look ahead, look at the temporal domain. So the ideal situation, you have to look at both. Your objective, obviously, you want to minimize the overall moving distance. And this idea is based on the dock station. So you have a dock station. What happens if there's no dock station? It's a dockless, means that the bicycle can scatter around everywhere. Then the complexity becomes higher because they have so many bicycles in the location. What we can do is doing some kind of virtual station. You draw a circle, like one virtual station, using the classic like k-means or clustering. Then you can apply the similar idea to that. So if you're interested, you can look at our publication last year. So some challenges, opportunities. There are many challenges. One interesting challenge I want to mention about this one. Suppose you have like two different areas. So you see the picture. So you can have two trucks to balance two areas separately. Suppose these two areas very close. So actually you can share the same trajectory, right? You have two trucks doing this in rotation. In this way, you can save some time. In fact, we did some optimization approach and to solve this problem. Although this one is applying the under the ocean, so deep sea data collection. But the idea is the same. Means that do you want to share the truck in the big area, or you want to have a separate trajectory for load balancing? And another interesting thing is about some kind of machine learning model, like how to predict accurately the data or demand, right? It's very important you know the demands. And also to come up with this kind of gaming or incentive mechanism. For example, in the previous example, our objective is to minimize the user detour when recruit worker to balance. So if user have a good experience, means they're really to small detour, means that there's more user willing to participate. When more user are willing to participate, your matching will be getting better. So it's a very nice feedback loop we call the incentive reinforcement. So let's look at the big picture. What's the future of bike sharing system? So we see this two type of dock and dockless. Theoretically, dockless is good, right? Because it's flexible for the user. But in reality, you may have an oversupply issue. Means that in a city you have too many bicycles. So this actually is a picture I took in Shanghai 4 years ago. So very interesting. You can see that the bicycles just pile up. So it's just ruining the whole areas. And so you may have an oversupply issue. So what's the current trend? And although we showed the picture that more and more cities using this bike sharing system, but some companies run out of business or they're in the financial crisis. Especially in China, there's the largest the dockless station is in financial trouble because just they oversupplies. So they have to sell this bike. They have to collect those bicycles everywhere. And another thing is that what's the future transportation format? So I classify those kind of format into two types. One's called active transportation. Active means that you may have a dedicated driver, like our current bus system, subway, right? And or you can have on demand. Demand means that you have a driver, taxi, Uber, and so on. So that means the driver can just go to the place where you want. So it's called on demand. Or you can have some kind of hybrid, means that you can have a fixed route. Fixed route means like a bus, and on demand is non-fixed route. Or we can come up with some kind of semi-fixed route approach. We call it hybrid. Again, this is a paper I wrote like 15 years ago, 14 years ago. If you're interested, you can look. And another type is so-called a passive approach. Passive approach means that the worker or user is the driver. So you can use a zip car, means that like you pick up a bicycle in a station. So you pick up a zip car in a station, or you can use like share bicycle, or right, or even can use a scooter. Obviously, with a self-driving car in future, things make it more interesting. Where a self-driving car is kind of active transportation or passive. And another picture means that what kind of futures for those kind of car and bicycles. So you see lots of called e-bike. Right? So it's or they have a scooter. So you have two wheels e-scooters. So what should be the future? So I showed a picture about like 12 years ago. I visited MIT Media Lab. They showed me a project they're doing called folded mini cars. Very interesting. So it's cars like you can fold, very, very small. Right? So you can those cars can be shared. So, but one challenge thing is that with this kind of car in future, or e-bicycle or e-scooters, do we need to, how about the safety and regulations? For example, nowadays in almost all cities, right? So you have like a pedestrian lane and bike lane or the car lane. So do we need to create another lane, or those like a small car should be sharing with a bicycle lane or with a regular car lane? So there are many other issues, not just the bike sharing or other things. So the safety is one of the challenges. So I think with this, I basically finish my talk. So if you're interested to know more about this project, last year I wrote a paper. It's called Challenges Opportunity in Algorithmic Solution for Rebalancing in Bike Sharing System. It's mainly what I talk today is about the summary of that paper with a focus on the algorithmic solutions, not AI or machine learning solutions. With this, I conclude my talk. Thanks for your attention.